This video is for topic 3.13, or the Beer-Lambert Law. The objective for this topic is to explain the amount of light absorbed by a solution of molecules, or ions, in relationship to the concentration, path length, and molar absorptivity. So we're going to use what's called spectrophotometry when we apply the Beer-Lambert Law. So spectrophotometry looks at transmittance and absorbance of light through a colored solution. Transmittance is symbolized by a capital T, and it is the ratio of the amount of light transmitted to the incident light. So the incident light is just the normal light that can get through a solution, and then the light transmitted is a specific beam of light that is sent through the solution. The higher the transmittance, the more light gets through. The lower the transmittance, the less light gets through. Absorbance is almost the opposite. It's opposite in concept. And absorbance can be calculated by the negative log of transmittance. And absorbance looks at how much light is absorbed instead of how much light goes through. Absorbance is going to increase as your concentration increases. So the more light that's absorbed, the darker your solution, the more colored it's going to be, which means higher the concentration. This law only works with solutions that are colored. It does not work with uncolored or clear solutions. So this needs to be a solution that results in some sort of color. It's often blue, green, or red-orange, because those tend to be the compounds that we use when we're looking at applying this type of law. So Beer's law, which is how we shorten or talk about the Beer-Lambert law, is the absorbance is equal to the molar absorptivity constant, so a constant, times L, which is the path length. So that would be, it's typically the length of your cuvette. Most cuvettes are 1 centimeter, times the concentration. So the absorbance is going to be directly related to the concentration of your solution. So we can use the absorbance of a known concentration of solutions to create what's called a calibration curve. So what we do is we prepare solutions of varying concentrations that we know the concentration of, and then we measure the absorbance. And we plot, and I'll show you a sample graph here in a second, we plot the absorbance versus the concentration, and we'll get a line, and we call that our calibration curve. Then if we have an unknown solution, we can measure its absorbance and then use that known absorbance to then calculate the concentration, because we can find where it falls on the curve. So this is what we're looking at when we actually measure the absorbance or transmittance of light. So a cuvette is a small, usually plastic, sometimes made of quartz, but usually plastic. It's not a cylinder because it's square. And we fill it with the solution, and then we put it in our little instrument, and it sends light through. And how much light gets through tells us about the concentration. And so it does account for some scattering and some reflection or interference losses by the cuvette. So those do factor in, but they're not something that we significantly worry about. So like I said, there is a linear relationship between the absorbance and the concentration for a given path length. This applies to, like I said, colored solutions, and it also applies to relatively dilute solutions. Once the solution gets too concentrated, it's not a linear relationship. So when you're planning out an experiment, you want to make sure that you have a range of concentrations that range from low to kind of medium, because as you get into a higher concentration, your calibration curve won't be a straight line. And so what we get over here on the right is what you might see for an example of a calibration curve. So we would take known concentrations and plot them with the measured absorbances, and then we can use an unknown to measure its absorbance, and then we would be able to calculate the concentration, because the molar absorptivity would be the same for each solution. So the molar absorptivity is going to be specific to a compound. It's going to be specific for that solution, but it's going to be the same if you're measuring the same solution. And then we pretty much always have the same path length when we do a Beer's Law experiment, because the path length is going to be the length of your cuvette, and we don't change the length of our cuvettes within an experiment. That tends to be a pretty standard size. And so then on the right, we have just another visual representation of how the particles interfere with the light. So when you have a lot of particles, they can absorb the light, and so the light doesn't go through and be measured on the other side. Whereas if we have a lower concentration or fewer particles, then you have more light that's allowed through.